The technology industry frequently fixates on the idea of a singularity, a singular, discontinuous moment where machines suddenly exhibit general intelligence. Artificial general intelligence represents a transitionary threshold on a technical continuum toward artificial superintelligence. This diagram from Google DeepMind's From AGI to ASI report formally maps the trajectory from narrow AI through general intelligence and into superintelligence. DeepMind structures this progression on a matrix. On the y-axis, we measure capability, the depth of a system's performance. On the x-axis, we measure generality, the breadth of tasks it can execute. Viewing AGI as a binary switch creates a blind spot. It obscures the actual mechanical forces that drive an intelligence explosion once that initial baseline is crossed. Looking at the bottom left of this matrix, we find Level 1, Emerging AGI. Current frontier foundation models, like GPT-4 and Gemini, are situated here, performing general cognitive tasks at the level of an unskilled human. Moving up the capability axis, Level 2, Competent AGI, matches the 50th percentile of skilled adults. Level 3, Expert AGI, reaches the 90th percentile across general domains. The theoretical endpoint of this taxonomy lies in the extreme upper right. Level 5, Artificial Superintelligence. Level 5 describes a system that outperforms large, well-coordinated institutions of experts working for a decade across virtually every domain. DeepMind models the transition from Level 2 to Level 5 as a collision. 4 technological pathways push the system forward, while 6 physical bottlenecks push back. Managing the transition between Level 2 and Level 5 requires a global engineering and safety effort across multiple disciplines. We can visualize this upward pressure as a central engine fed by 4 technological pathways. Lane 1 is scaling, compounding larger models with massive compute and training data. Lane 2 is algorithmic shifts, moving beyond standard transformer architectures to process information more efficiently. Both scaling and algorithmic improvements currently require human engineers. They depend on human labor and are subject to linear human timelines. Human-driven pathways alone cannot achieve the growth rates required to reach Level 5 ASI. A non-human accelerant is required. Lane 3 is recursive self-improvement, or RSI. This mechanism facilitates an intelligence explosion by initiating 3 distinct feedback loops. The first is genotypic improvement. AI optimizes its own base architectures. The second is mimetic improvement. This occurs when AI systems autonomously generate and distill their own synthetic training data. Like AlphaZero's self-play, this extracts human data production from the equation. The third and final feedback loop within the engine is sociogenic improvement. This involves specialized multi-agent AI collectives autonomously dividing labor. They coordinate as a digital supercorporation, maximizing output without human management overhead. These software loops are multiplied by the 4th pathway, AI directly designing faster, more energy-efficient hardware. When an AI can execute the work of an AI researcher, the loop closes. The human is extracted from the iteration cycle. Recursive self-improvement replaces human research with an autonomous chain reaction, turning intelligence into a self-accelerating output. This engine operates inside the physical universe. DeepMind identifies theoretical and physical walls that act as a counterforce. First is the data wall, exhausting high-quality human text, and the resource wall, encompassing the massive demands for energy and hardware. Next is the paradigm ceiling, where pre-training large models hits diminishing returns, and research difficulty, where undiscovered breakthroughs require exponentially more effort. The 5th bottleneck is deliberate slowdown. Regulatory actions or societal backlash can artificially restrict capability progress. Predicting the arrival of ASI requires calculating when these digital growth curves will collide with the constraints of economics and physics. The 6th bottleneck for digital ASI is the abstraction barrier. DeepMind researcher Alexander Lurchner formulated the hypothesis that AI models trained on human cognitive products are permanently bounded by existing human conceptual frameworks. Current foundation models excel at recombining human symbols to pass standardized tests. They lack the mechanism to independently observe raw phenomena and extract a novel physical law from scratch. Breaking through this conceptual boundary requires overcoming the embodied bottleneck. To discover a novel physical primitive, a superintelligence must validate its digital hypotheses by executing empirical experiments in physical reality. This reliance on empirical science forces the software back onto a physical timeline. Chemical reaction rates and physical mass manipulation operate at a fixed speed, injecting latency into the self-improvement loop. Autonomous self-improvement loops remain rate-limited by the speed of physical reality, acting as a physical brake on recursive software scaling. If synthetic data and autonomous robotic labs allow the RSI engine to bypass these physical bottlenecks, the safety profile of the system changes. Nick Bostrom outlines this risk through instrumental convergence. Any sufficiently advanced AI will naturally develop instrumental drives, specifically self-preservation and resource hoarding, because those drives are useful for completing any goal. We can evaluate our preparedness for this risk by looking at the April 2025 OpenAI Preparedness Framework. An affordance analysis found that the framework requests evaluation of critical risks, like biological weapons, but never strictly demands them. Furthermore, it allows and encourages deploying models with medium capabilities for severe harm, defined as enabling mass casualties or $100 billion in damage. The policy also contains a structural loophole. It grants the CEO the authority to override the risk recommendations of the company's safety advisory group. Voluntary corporate frameworks built on allowances and requests are not equipped to contain a self-improving superintelligence driven by instrumental convergence. The next decade of computing is defined by the collision between recursive self-improvement and hard physical limits. Because of this friction, the trajectory from level 1 to level 5 will be a jagged path, defined by these conflicting forces. The move toward ASI results in a turbulent cascade of systemic shocks across science and technology. Reaching level 2 AGI is merely the entry point. The engineering challenge lies in managing the transition horizon that follows it. The central technical uncertainty remains. Will sociogenic RSI bypass physical limits, or will the abstraction barrier cap digital intelligence at the human limit? Whether the physical brakes hold or the RSI engine explodes, surviving the transition to ASI requires rigorous systems-level engineering, not reliance on voluntary corporate guardrails.